how can we see a newborn star? Well, the process starts in a cloud somewhere like this. This is where stars are formed, in vast clouds of gas and dust. Now, it might look quite thick and smoke-like, but in fact, it's more than 1 trillion times less dense than the air that we're breathing in now. The process starts when you've got a dense clump of this gas, and it starts to squeeze together under its own gravity. And you can see at the top one of my computer simulations of this happening. And as it squeezes together, it gets warmer, and there comes a point where we get a ball of gas that's warm enough that it can support itself against collapsing further. And that ball of gas is really the newborn star, because it's that will carry on developing to eventually become a fully fledged star. Now, this one is rotating, so it's developed some really beautiful spiral arms as well. We'd really like to be able to see one of these things in real life, but we haven't yet. And that's partly because they're still buried deep within the clouds that they're formed from. They're also still very dim, and they also look a lot like more developed protostars, so it can be hard to tell the difference. One way that we might be able to tell the difference, though, is through chemistry. It's a bit like this. So if you think back to the last time that you made custard. So you heated up some milk on the hob, you took it aside, you stirred in the custard mixture, put it back on the hob, and you stirred it around in the pan. And the mixture is still very thin. And then all of a sudden, it thickens. And that's because it's reached a certain temperature where a chemical reaction that thickens the custard can happen. And the same thing happens where stars are forming. We've got a huge range of temperatures from like nearly absolute 0 to 1,000 degrees, and an even bigger range of densities. And that means we'll see different chemical reactions occurring in different places, and then we'll get different chemical products formed. And we can already observe different chemicals in star-forming regions, because each chemical gives off light at a particular color or wavelength. Astronomers can look at what chemicals we have there. For example, they found nice things like water and not so nice things like formaldehyde. And what I would like to do, is what I'm doing, is taking the information on the physical conditions from simulations like this and calculating over 6,000 chemical reactions to see what chemicals we'd expect to see forming in different parts of the object. And this is what I find so far. So we've got on this side this giant blob, which is cyclopropylenediene. I hadn't heard of it either until recently. And it looks like a big blob because it forms in the lower density envelope around that central object. And at the other end, we've got sulfur monoxide, which looks really compact because it only forms in the warm core. So it shows up the core of the object, of the newborn star, really nicely. So if we know what chemicals to look for, that could help astronomers to be able to identify a newborn star for the first time. Thank you.
Thank you, Alison.